Alright, so here we are with Chapter 6, Section 3 for Algebra 2, and we're talking about functions and their inverse. So, our objectives today are to determine whether the inverse of a function is a function and write the rules for the inverse of functions. So, first thing that we're going to do is talk about a vertical line test. Let's see. I'm going to make a statement down here in the vertical line test paragraph. So this is the one that you are going to use always. And it's going to use always on the original function to determine if it is a function. Or we can use on inverse function to determine if it is a function. Alright, so we use it on an image on a graph to see if that thing that we're looking at is a function. So what is the vertical line test? So we do call it the VLT. So the vertical line test is to draw a line, of course a vertical line, on a graph if the line touches the graphed equation at more than one point. It is not a function. Alright, so that's your vertical line test. Then we have the horizontal line test. And usually we avoid this one because you may as well just look at the vertical line test of the original function. But you use it on the original function to determine if its inverse is a function. So taking a look at this, I'm using the vertical line test. Potentially you're just drawing them yourself in your mind. And there is, even though it does get very vertical, there is no way in that red function there that it wouldn't pass the vertical line test. So we do have a function on that red graph. However, if we switch to the horizontal line test, we notice that we do in fact have a line that touches the graph in fact 3 times at some points. So on those ones, that means that you end up having the inverse of that red function not being a function. So again, the issue is that it's not for what we're seeing, it's for what we're not seeing, which is its inverse. This other one here, option A, you may think that if we draw option A, it looks like there is a vertical line that would touch the equation more than once, but no matter how far you zoom in there, it will actually only ever touch it at one point. And so it is a function, and then if we switch to the horizontal line test, its inverse will also be a function. There's no horizontal lines that we can imagine as we're drawing this that would touch it more than once. So The next thing that we're doing is actually making the the inverse function. So how do you write an inverse function? The first thing that you would do is take f of x and change it into y. It's a lot easier to maneuver when we have just a variable instead of that function notation. So y equals x squared minus 4 is our first piece. Then the next thing that we would do is actually switch x and y. So the two variables we're switching. So x is going to equal y squared minus 4. Then we end up solving for y. So we're going to undo all of the operations. So for instance, I will add 4. And again, this is SADMEP that we're doing to undo. So I'm going to add 4, get an x plus 4, and then square root to get y equals square root of x plus 4. It turns out that depending on what was the y value, it could actually have been a negative or a positive. And so because of that, when you're solving, you actually do need to keep a plus or a minus here because of the fact that this, while solving, could have been squared and therefore originally could have been positive or negative. So then the last step here is to take your y and change it now into f with a little tiny 1, which means inverse. And now we have f inverse equals the plus or minus square root of x plus 4. And so that is the inverse function. So what does that mean? It means that we now have a function that will undo all of what the previous one would do. So then we go through and we determine, is that inverse equation a function? So we could graph the inverse on an actual number line, graph, and then we could use the vertical line test. We could graph the original equation and use the horizontal line test. And we could also look at the graph and notice that the original function versus the inverse reflect over the y equals x line. So, just so that we remember, the domain is the x values of the original function. The domain of the inverse function is the range of the original function. So, we'll talk about that when we graph it. So, the idea here is that I'm going to graph the original function. So I'm going to graph x squared minus 4. So taking a look at x squared minus 4, plugging in negative 3 means negative 3 squared, which is positive 9, and 9 minus 4 leaves us with 5. If you plug in a negative 2, we're going to get 0. Negative 1 is negative 3. 0 is negative 4. 1 goes back up to negative 3. 2 goes back up to 0. And 3 goes back to 5. So if we graph that equation, we're going to have negative 3, 5 up here. Negative 2, 0. Negative 1, negative 3 right there. 0, negative 4. And then 2, 0, and 3, 5. So we have this quadratic, of course, because of the squared equation. Alright, now the interesting part, as we kind of mentioned here, is that it's going to reflect over the y equals x line. And so if I draw the y equals x line, which goes through over 4, up 4, over 5, up 5, these lines here, or this reflection line here, this becomes the mirror. And so you end up with something like this, reflecting across it. Because again, you kind of need to rotate your image to kind of see how that would work. So, turns out that the easiest way to graph this is to understand that the domain, which are the x values of the original function, are actually the range when we get our inverse. And the range of the y values of the original function, the range of the inverse is the domain. So basically they flip. So that means all I need to do is flip my x's and y's, and so now I'm going to say that these are my x's and these are my y's, and use this same table going backwards. So for instance, I'm going to go over 5 and up 3 to graph this point. So over 5 and up 3, there's a point right there. And then over 0, up 2. And then over -3, up 1. Over -4, up 0. Over -3, down 1. Over 0, down 2. And over 5, down 3. And so hopefully you can see, especially if you turn your image sideways, that this very much looks like a quadratic. In fact, it's a quadratic that has been reflected over the y equals x line. And so that is your inverse after your original. All right. So what does that have to do with what we did in our last section? Composition. So we're going to use composition to verify that what we have are inverses of each other. So we need to plug in our inverse into our function and plug our function into our inverse. And if both solutions are just x, so if everything cancels and it's just x, that means that we do have inverses. So, taking a look at this example here, I'm going to insert one equation into the other. So the first thing that it says to do is do f of the inverse So I'm going to write the original function, 3x minus 1 squared. Then I'm going to erase the x and replace it with what we assume to be the inverse of the function. Alright. Then we're going to do kind of a bit of interesting math, but that is totally okay. So here we go. And actually, I'm going to do what we did before in order to prove what we did before is an inverse, because this one gets a little bit too much. So I'm going to use our previous equation of the original equation of x squared minus 4. And then the inverse equation that we got, which was plus or minus the square root of x plus 4. Just double check. Yeah. Alright. So this one's going to be a little bit easier to identify. And of course we know it's an inverse because we solved it, but let's just double check that it is. So what I need to do again is find f of the inverse. So I write the original equation, erase the x, and plug in my inverse equation. Alright, so even though there is a positive or a negative, if we square a square root, we're going to end up canceling that and becoming x plus 4 and then minus 4 ultimately. Negative 4 and plus 4 becomes just an x. So we have that f of f inverse of x equals x, because those two cancel. Alright, so then the next one I'm going to do the opposite, so now I'm going to take the inverse and plug in the original equation. And if this one equals x, then we know that they are inverses of each other. But if it equals x squared, or x minus 1, or 2x, then it's not an inverse. So let's write the original outside equation, so the inverse. And then we're going to erase the variable and plug in the original equation of x squared minus 4. Then we see that minus 4 and plus 4 can cancel, so we're left with plus or minus the square root of x squared. Then the square root and the square are going to end up canceling, and so we end up with f inverse of f is equal to x. And so because they're both equal to x, then they are inverses of each other. Which of course we knew because we were the ones that created it, but at the same time it's nice to then get the idea that what we did was right. So on your assignment you are going to have a few of these problems. So what's going to happen is you're going to, for instance, have to identify if something is a function, or if something's inverse would be a function. So that's where you're going to talk about the vertical line test or the horizontal line test, and identify if that equation or its inverse is a function. Then you're going to be asked to write an inverse, so they'll give you a function, and you're going to have to write its inverse. You'll also be asked to make the mirror image, or the inverse, based on a graph. So if we look at a graph, it reflects across the y equals x line. Or they might talk about what is the domain and range of one function versus its inverse. And so you will know to then switch the domain and range. And then lastly, they may have you verify that something is an inverse of another. And so all you need to do is find the composite of both of them, and hopefully they both equal x, because then they are inverses. Otherwise they are not.